Okay, welcome back. So let's continue with this tutorial. So now let's move to Fluent. So remember, we are going to work here within the workbench. In the next videos, we are going to get out of the workbench, but this setup will be the mesh. It will be the same. The only thing that you need to fish the mesh, whatever you put it here in this folder. Okay, so in my case, I will open this one. It doesn't matter. So remember, when you click here, Fluent will open automatically will recognize the meshes 2D, 3D. Here always choose double precision, number of processors, so I will put 4, and that's all. You don't need to set up anything else. You don't need to give the path, nothing, okay? Workbench it knows where all the files are located. So let's launch, and here's launching. Now it's launching Fluent. Okay. So as you see here, it's clear that you're using more memory. You have the workbench that is already taking some computer memory and also hard drive space, saving all this backup file plus Fluent. Okay. So this is why I don't like to work with Fluent if I don't need it. Not with workbench if I don't need it. Sometimes you need it. Now, so you're doing like parametric stuff, but most of the time you don't need it. So it's better to work standalone. So see here that you have the mesh, and let's go back here to the case presentation. So you have all the properties, everything, boundary conditions. Well, look at here that I'm telling you to scale the geometry. Okay, so this is very important. Now, always when you are opening the mesh here, always check your dimensions. So if you go here in scale, see here that you have your dimensions. So always check that you have to the dimensions that you created. The domain sometimes might happen conversion something or comments from somewhere else. You might have different dimensions. So always check that you have the right dimension. And if you want to scale, just go here. So for instance, you can convert from meters to feet to millimeters, whatever is up to you. In our case, we want to multiply by 0.1 in all directions. See that you press scale, and now you have scaled your domain. Okay, so see that it is out of this view. So what you need to do is just replot it, and now you will have it scale. See that you have the right dimension. So see, this is what I was asking you here. Okay, so here you see that how you can do the scaling, but remember here also you have transformation. You can translate, rotate your domain. It's up to you. Also remember here in quality, evaluate mesh quality. You have it. So usually 2D is always you're going to get good quality meshes. In 3D is where you start to have problems. But I mentioned that this is important value. And let's say if good meshes, this value should be 0.0, more than 0.01. Less than that means that your mesh, you have quality problem. Doesn't mean that you cannot run, but maybe you may have some artifacts in your solution, something that will affect your solution, okay? Might be, might not be the case, okay? But usually 2D meshes are okay. Also in 3D, the Ansys measure works really well. So you go here, also you have here like the number of cells, you have some general information, okay? So here in this tab, you have all that stuff. Okay, so let's set up the case. Remember that we have this vertical workflow, but also you can do it here in the ribbon. I don't like to do it here, but I prefer to do it here. So let's go here. So we have here our case setup. So see that I'm asking you working fluid, it will be water, liquid water, and actually it's important, or liquid water, because also you can have water vapor, okay? So those are more models that you have in Fluent. See that I'm giving the density and I'm telling you that the models are constant. So these are thermodynamical models, okay, and boundary conditions. So let's go and set up this. So here, the default values are okay. We want to run a steady simulation, models. So let's start to enable models. So viscous, this is okay. This is one you can choose something else. And energy, we want to enable energy because here see that I'm telling you that we have temperature. So you need to enable the energy equation. So click here, okay, and now we have energy equation enabled. So if we go to Fluid, see by default, Fluent, okay, it picks air. So you can define your values here. So see that if you want to change these values, and you can give it another name. So I will call it, for instance, banana. Change create, Okay, and say that you call it banana, banana, and then you start to put your values. Okay, but also you have access to the Fluent database here. So as you open there, you'll have many, but as you go to the bottom, see here you have water liquid, copy, and now you add water liquid to your database, and here you have all the properties. Okay, so by the way, the values that you see here are the default values, so you don't need to change anything here. But see here that also you have access to models. Okay, so if you want, you can put this one in compressor gas, or if you have a polynomial law here, you can give the coefficients. So you define that there. So in our case, everything is constant. Okay, so we have all models constant. So in theory, as density, CP, thermal conductivity, viscosity is not changing with temperature. So the temperature that is entering the flow, the hot and cold flow that are entering these boundaries will be like a passive scalar, okay? So later we'll show you that instead of enable energy, we could have added a passive scalar. So let's work here. So you set up your new material, but it's important that now you need to apply this new material to your domain. So as you click here, see that you have a domain, you open edit here, you need to tell that you want that material there. Okay, be careful that by default it will not pick up that one. By default would take air, I rename it, but now see that click there, now you are applying that material, that new material into your domain. Then you move to boundary conditions. Okay, so remember that you gave those names. So let's do the setup. So we have inlet 1, that is this one here, will be 0.4 from 20. So 0.4. Okay, so I will use these default values. Remember, it's up to you to pick up something else. And temperature, you set it here. Okay, so see that I'm telling you here 20 Celsius here. By default you use Kelvin. So now I prefer to work with Kelvin, but if you want to work with Celsius, you can change units. So just to show you that, so you go here in domain, see units, you can choose the unit. So you have many quantities there. So for instance, in our case will be temperature. You look for temperature, yeah, and choose the new unit. So you want to work in Celsius, and that's all. So as you go back here, you now have it there in Celsius. So put that one. Then you have also inlet 2. Okay, so by the way, let me go back here. So important that here is magnitude normal to boundary. Okay, so normal to this boundary. You can also give the components. Okay, so usually normal to boundary. Okay, then you go inlet 2 is the same. Okay, what you are going to do here, if I will recall, it was 40. Okay, and the velocity is 1.2. Okay, so here will be 1.2 normal to boundary, and I will use these default values. Okay, then we go the rest. So wall is a wall. Okay, so see that Fluent created automatically this group. Outlet is a pressure outlet. Okay, it's okay. Fix your pressure here 0 or whatever value you know. So probably you have here negative in the pressure, so it's up to you. Usually you fix it to 0. It's relative pressure, okay, relative to to the reference pressure. And in thermal also you have this case. This is for backflow, so always pay attention to the word backflow. As you see, backflow means that in the case that you have if you had here a flow coming back to your domain, Fluent will assign this value to whatever is entering. Okay, so it's up to you. So usually I like to put there an average. So my average between inlet and outlet, let's say, will be 20, and here that is okay. Now we keep moving, nothing to do here, nothing to do here. Reference values, remember this is for the non-dimensional coefficient, so I will use free stream values from inlet 1. So see that it's using the velocity from inlet 1 that you will have. Okay, y is 0 here, so I have a problem with inlet 1. Okay, so it will be 0.4 and 20, and here 1.2. Okay, so now let me select. So see that now. So I'm using free stream value from inlet 1 to compute coefficients if I want to use them. Nothing to do there, nothing to do here. Now solution. Solution default method is okay. So I want to point out here when I show you this slice here, that the solution first order and second order accuracy. So see that in the momentum equations, you choose a first order algorithm method, you are too much numerical diffusion. This is unacceptable for final solution production runs, okay? So always choose at least second order accuracy. So that refers to this one, okay? So see here that you have third order, we're going to see this later, but this is too diffusive, okay? So it's a good idea, second order momentum and also energy. Then turbulence quantities is one, to add stability, you can put it first order, but usually what Fluent proposed, it is okay. So see here that everything is second order accurate. Then controls use the default values. Report definitions, you can create a few reports. So I will create the usual one. So I will create one for, let's say I want to compute the average y plus value. So let me go at the wall. I will say y plus average. And then turbulence and choose here the y plus. Report to plot, and okay. Then let me choose, for instance, average temperature at the outlet also. So I'll go here, it's pretty much the same, surface, phase average. Okay, so let's do a mass weighted average. Okay, remember that, well, it doesn't make a difference because here it's constant now, but usually in temperature you like to use mass weighted for compressible flow. So temp average, okay, and you want to compute it at the outlet, report to plot, and that is okay. Oh, sorry, here you need temperature, static temperature. So see that now I'm monitoring that, and let me add also the usual mass flow, the imbalance. So if I go here, flux report, see here that you go mass flow rate, and you can select here, here, and here. Okay, I will call it imbalance 1. Okay, so this one will do this plus this plus this. Okay, so negative is going out of the domain. So let me put it here and let me add a second imbalance just to show you also flux report. So I will call it imbalance 2. It's pretty much the same, but here, see, now I will choose person. Means that now are independent. So if I go back to the plots here, see that person will plot this line for each of the surface patches I chose. Instead, if you don't select that one, it will be not just the summation of all that, all those values, just to show you. And that's all, okay? So you want, you can add more monitors. So see here that showing some examples on sampling. So here also we're doing some sampling in a line here, okay? So I don't recall the distance, so I will throw a value there. So for instance, that, okay, so let's finish here. You have your report definitions. Okay, now that's all. Monitors, you have everything, you are set to go. If you want to create that sampling line, so you see here, your domain goes from, okay, from this value to this value. Let's put something in 0.3. So you go here, new line, and you just can put the values there, 0.3, 0.3, and this one, let me put 1. Let me see this line. Okay, you have the line there, probably was too large, 0.2. Okay, it's short, okay, 0.6. Okay, so here, okay, increase this one. And this one will be this. Okay, so see that perfectly. Okay, you have the line covering. You can do the sampling. Remember, not necessarily needs to be needs to match perfectly the extreme. So you can have it like this. There is no problem. So here there is no solution. One sample. So now you created that line and you can do your sampling. So at this point you have set up everything. Okay. So in this case I will focus more into running to the mesh. I'm not going into detail for doing all this turbulence modeling sampling. We have it done in the Pi, so you Pi cases in tutorial 1 and 2, so you can follow the instruction. Also, you have the setting file where everything is set up, so you can reproduce that easily. So at this point, let's run. if I press now here, let me put here a value. So remember what is stop when it reach this tolerance that you have in the residuals, or if it reaches the maximum number of iterations. So you press calculate, yes. And now it starts to run. So you saw your residuals, your y plus average. So see that this mesh is getting something about 8, the average value of temperature at the outlet, the imbalance, the total imbalance. So see the reach convergence. And here, okay, so you have per zone here, different zones, and this is here then the summation, the total that should be value close to 0. So see that reach very fast convergence. So let's run it a little bit more, and let me reduce this one like this. Or you can switch it off, it's up to you, but I want to run a few more iterations. And that's it. You have your solution, and now you can do your traditional post-processing. So you can plot static pressure, you can go for velocity, okay, or remember that you have temperature. So see that you have, and this is what I'm talking about, cold and hot flow. And see here that here is the mixing. So here you have an interface. So that interface between the two streams, okay, is dependent of the mesh. So if you have a very fine mesh, this will be a sharp interface. So remember that here, everything is constant, okay? So this should be something very sharp, okay? Now let me hide there. And this is it, okay? So now you can access also all your properties, turbulence model, everything, you have it there. So if, for instance, you want to plot in this line, you go plots, swipe plot, pick up the line, and for instance velocity, and see this is the velocity profile along that line. Okay, so see here, this you can clearly see here the secondary line. As you put temperature, you will see that hot and cold. Okay, so in this case, this should be a very sharp interface, but we have a diffusion coefficient also. See that it diffused a little bit. But in the next case that I will show you, a passive scalar, we're going to put the diffusion coefficient of that passive scalar equal to 0. So this should be a discontinuity, like a shock wave, so like sudden change. But due to the mesh numerical consideration, there is a little bit diffusion, okay? But what is interesting, that let's rerun this case, okay? And let me go here, and soon here, let me save this image. So in my case, so probably you have different bars and your installation. I already moved everything, so I have it like that. So let me save everything in my desktop. So let me save this image. Okay, so I have it there. Okay, and let's rerun this case just to show you the difference when you run with first order accuracy and what is the problem. So now let me rerun. So remember, the only thing that we need to change is the discretization here in methods. So now if I go here, first order accuracy, and let's start from scratch. Okay, from 0, and calculate. So now we're using a different method to approximate the momentum equation, the convective terms in the momentum equation. So see that convergence is very nice. Like the previous case, we have a solution. So now let's look at the solution here. Okay, let's see the colors. Okay, so let me save. This one probably is difficult to see in this case, maybe. Okay, now I think. Okay. I think I didn't add it that. So first order momentum. Let me go also energy equation, just to show you here. Okay, so there is a difference, but it's difficult to see there. So let me change everything to first order there. And let's rerun. So hopefully here will be more evident now that numerical diffusion here. So okay, here already so see here the problem is this. Okay, too much numerical diffusion. Okay, so here I set everything to let me change here and let me go here. And see, second order accuracy, first order accuracy, and clearly you see the difference. The same stuff that you see in these slides here. So that's why we don't want to use first order accurate method. They are very stable. Okay, so they still exist there, and you have it there because they are very stable. Let's say you are dealing with shockwave, you want to use those methods just in the area where you have the shockwave. But in this case, there is no need to go first order accuracy because it's too diffusive. Okay, so it's very important, this one. Okay, keep it second order and energy as well. This one you can run first order, shouldn't be a big of a deal, just to show you again. So let me initialize again. And let me go here, calculate. So we start and see that nothing changed. The residuals are also cool, very nice. But also here, all your quantities, monitoring. Okay, so see that now I only left second order accuracy or first order accuracy for the turbulence quantities. Okay, so see that pretty much the solutions are very similar. Okay, the big difference is made when you choose first order accuracy for these two, for momentum and energy. Okay, this you need to go second order accuracy. This one you can use first order accuracy. So at this point, okay, in this slide in the PDF, see that you have many plots. Try to reproduce these plots. Okay, so the way to do this one exactly the same as the previous case. So see here that you sample wall shear stress here, put the line. Remember, starting from here, it should be the 0. Okay, so I will show you have the settings there. So when we do the standalone Fluent case, we're going to do it. So just to show you how to do this as well. So to do the vector plot is also straightforward. Now you go here, vectors, and select where you want to plot. So I want to plot the vectors in the line there and the outlets, save, display, and you have it there. Or if you didn't select anything, we'll plot everything in your domain. Be careful that if you are in 3D, likely 3D with a large mesh, it will crash, okay, because you have too much information. So here you have these options to skip. Now, so you put 5, you are skipping 5 there. Okay, so be careful now. Depends, you know that you have a lot of cells. This can crash your computer. So see that you have the second string entering there. Okay, so just to show you something that, well, I will show you in the standalone more advanced post-processing. So see here that velocity, and see here that even the mesh it's not perfect, it's not super fine, but it's interesting to see that here it managed to capture here there is a recirculation, and here also. Okay, so this is the turbulence model. So now if you try to run this case laminar, you will see that you will get very different behaviors. Likely the case won't converge. Okay, this one will remain stalled. There will be a lot of oscillations there. Okay, so try to do it in laminar. So yes, this is all for this case. Okay, so as you go back here, let me close now. It will save the solution. You have the location in the directory and everything. Okay, so if you want, you can run everything also here. But now in the next video, we're going to get out of this workbench that I don't like to use it very often, I already say that. But we are going to use just the mesh. Okay, so we know that this mesh is located in sys1. Okay, so as you go in your case here, you should have dp0 sys1. And here you have the mesh. Okay, so we're going to take the mesh, any of those meshes, and then we're going to set up everything outside Fluent. Okay, so in the here you have the settings. You can download the settings. Okay, and we're going to apply these settings to the mesh. Okay, so we're not going to do all this setup again. Or if you want here, remember that when you set up this one, here you have the setting files, should be this one. Okay, so you can copy this file. So you say open container folder. Okay, so this file, put it somewhere where you are going to copy the mesh, and this is the settings for your case. So that's all for this case. Thank you for your attention. See you next video. Remember, next video we're going to get outside Workbench. Okay, so thank you. I'll see you next time. Bye.